So in section 4.4, we're going to look at something known as concavity. And after we understand concavity, we could use the first derivative test that we learned last time to figure out some basic curve sketching techniques. And honestly, 4.4 is going to feel very similar to 4.3. We're just going to need to take one more derivative. So we'll have to use the second derivative. So let's go ahead and just recall the first derivative test and what it tells us about a function. So right here, we have a cubic function. Just recall a cubic function has the end behavior that it goes down on the left and up on the right. And the most basic cubic function has this shape. And again, we can see it more explicitly and cleanly written down here. So what does the first derivative test tell us? Well, if we take the first derivative, we find that f prime of x is equal to 3x squared. And one thing that we did last time is we just set this equal to 0 and we solved for x and we found that x equals 0 is a critical point. Of course, then the critical point allowed us to break up the domain and then essentially just think about, well, it was increasing here and increasing here after we plugged a value in like f prime of -1 and f prime of 1. So again, the first derivative test said the graph continually increased. And you could also think about this in terms of if you just look at this function, that function is always positive, so it's going to always have a positive slope. And you can see there is no local extrema on this graph. But what is interesting is still kind of what's happening right here in the middle. So right here in the middle, we want to go ahead and think about, okay, what is happening at x equals 0? And that's really the question we're asking down below. What if we want to know something about the rate of change of the rate of change? Are we accelerating really fast? Or are we a little bit of a slowpoke when it comes to driving? The rate of change of the rate of change, AKA the acceleration, if you're thinking about it in terms of like a physical application. So let's go ahead and consider the rate of change of the rate of change. That is to say the second derivative. So f double prime of x is equal to 6x. And if you, again, take that same idea and think about setting this equal to 0, you again find that x is equal to 0. So this is not a critical point at this time, and we're going to go ahead and define this here shortly. But if we look at what's happening at x equals 0, we have essentially a leveling off of the rate of change. So what we'll see on the left-hand side, if we were to go ahead and do this kind of same idea where we break the domain of our function up into two pieces, but this time plug a value of -1 and a value of 1 into our second derivative, we find that this is negative and this is positive. So if we're thinking about what is happening right here, because this is negative, our acceleration is decreasing. So in other words, our tangent lines are becoming flatter and flatter as we get closer to 0. So let's zoom in here. If you look at a tangent line right here, notice that it has a slope that is steeper compared to the one that is right there. So there is this idea of that the m of this one is going to be larger than the m of this tangent line. And then what we'll find is that it basically reverses direction right here at 0. So we use the word concavity to describe this phenomenon, concavity. And you could think, it's a little hard to visualize since I can't put my hand on the graph and show you, but you could think about this. If you have a hand, it looks like a bear claw, but it'll work, and place it on here, the palm will be facing down. Where if you were to go ahead and just take this bear claw and place it smoothly on this part of the graph, your palm will be opening up. So that is one way to understand concavity. You're resting your hand on it, and if your hand is facing down, you're concaving down, and if your hand is facing up, you're concaving up. So of course, this is this process right here, which we'll now make formal, is known as the second derivative test for concavity. There's actually another second derivative test that we'll look at a little bit later, but the first one we're going to look at is for concavity. So it's pretty straightforward, and I really kind of informally did it right here, is you're going to take the second derivative, you're going to find where the second derivative is equal to 0, and then you're just going to see if it's positive or negative on the different sides of the 0. So let's go ahead and do one more example where there is maybe no change in concavity. That is to say right here, f of x equals x squared. So again, we're going to just apply the second derivative test for concavity in this example down below. So we're going to need to take two derivatives. So f prime of x is equal to 2x, and f double prime of x is equal to 2. So don't let this throw you off, but again, there's really no way you can solve this for x because it's a constant function, but note that it's always positive. Just kind of like that same principle that we talked about above with the quadratic, it's always positive. A constant function is always positive. So what does that mean? That means our original function, x squared, is always concaving up. So it always concaves up. So there is a possibility that just like when we looked at the first derivative test, that there was no change in increasing or decreasing, there may be no change in concavity. So let's go ahead and actually give a name to this point that we could find this point that we could find using our second derivative and setting it equal to 0. So again, we're going to find a name for this. That name is referred to as a point of inflection. So a point of inflection, so this differs a little bit different from a critical point. This point of inflection is actually a point on the graph. So like it's a value x, f of x, where the graph of the function has a tangent line. So we actually have to be able to take the derivative. This just means that f prime is differentiable. And the concavity changes. So this is important to note right here. So what we find when we set it equal to 0 is a possible point of inflection. It's not till we actually see if there's a change, if it's actually referred to as a point of inflection, a point where the concavity changes. So let's go ahead and look at this one right here. So we're asked to determine the concavity of y equals 3 plus sine of x on this closed interval from 0 to 2. You can see it's the blue graph down here on the right. So let's go ahead and do this second derivative test for concavity to see if we have a point of inflection. So let's take two derivatives. The first derivative is just going to be 0 minus cosine of x. Incorrect, it's going to be plus cosine of x because the derivative of sine is positive cosine. And then the second derivative, f double prime of x, is going to be minus sine of x. Now, let's set this equal to 0. Minus sine of x equal to 0. Of course, when we solve this, we can just drop the negative. So we just have sine of x equal to 0. And now let's think about this. In this interval, where are the angles where the y value was 0? So if we're thinking about our unit circle, our y value is 0 here and here. So that means our solutions are x equals 0, pi, and 2 pi. And again, this is a closed interval. So this is so we consider all three of those solutions. We actually include the endpoints. But realize if we are actually trying to determine the concavity, and kind of looking at the points of inflection, we don't have any graph off to the left or the right. So there's no way to even consider if there's a point of inflection there. So if we're asked to determine the concavity, what we're going to do is set up our domain put it up into 3 pieces from 0 to pi. Actually 2 pieces because we have 3 possible points where the concavity could exist. or what it could be defined. So it could be, we're going to be looking from this at this part here, and then we'll also look from pi to 2 pi. Before we actually do the test, let me just go ahead and say a quick thing about the point of inflection. We have not found the point of inflection yet. What we have to go ahead and realize is that points of inflection cannot occur at endpoints because there's no way to see if there was a change. So what we have right here is that that pi comma f of pi, so plugging it back to the original, is a possible poi, or point of inflection, but I'm going to say that, write that several times today, so let's shorten it. Sounds like a fish. Oh, because koi, never mind. All right, so again, this is a possible point of inflection. It's not necessarily a point of inflection until we know that the concavity changes. And if we're looking at this visually, you can see that we're expecting the concavity to change because you can see we place our hand in this facing down here, our hand's facing up here. So let's just, of course, verify that concavity did change at x equals pi. So what we're going to do is we're going to take some value and plug it into the second derivative. So let's do f double prime of pi over 2. And if we look at minus sine of pi over 2, we see that this indeed is going to be a -1. So let's go ahead and say, what is the concavity on this first interval? Well, it's concaving down. So it has this concaving down. And you can see that from 0 to pi, the graph, essentially, if you put your hand on it, is concaving down. I gave everyone bare hands today. All right. Now, if we were to consider f double prime of, let's say, some value between pi and 2 pi, let's say 3 pi over 2, when you plug this into the second derivative, you get, you're going to get a -1 or +1. So our concavity is up in this case. And you can see that from 0 to pi over 2, we do indeed have a graph that if you were to place your hand on it is opening up, so it is concaving up. So what does this mean? Because the concavity changed, so notice there was a change. Because of the change, we actually have a point of inflection, which in this case, as I mentioned above, is pi f of pi. And of course, we could figure out f of pi. And notice f here is our original function. So in that case, it's going to be pi is our x value, and 3 plus sine of pi is our y value. And then, of course, this is just going to go to 0. So our point of inflection is pi comma 3. And you can see right there, this is our poi. So that is how you find points of inflection, and that's just kind of the definition, that you still have to make sure that there is a change in concavity. So we have a few more examples we can go through, but let me go ahead and pause just for questions. So we have several more examples that we're going to look at as we include other ideas. So I'm going to leave you to try this one down below, and I would encourage you to maybe pause the video really quick, give it a try. And go ahead and give it a try. I'm going to put up the solution here in a sec. All right, so there's the solution. Again, if you need to check your work, just go ahead and pause it. But let's go ahead and look at the next problem. So the next problem as well, it's going to be on a new concept. So we have 2 types of second derivative tests. We have one for concavity, then we have another one for local extrema. So this will actually feel pretty natural once we understand what we have to do here. So suppose that you could take the second derivative, it's continuous on an open interval, and it contains some x value c. What is that x value c? Well, you can see over here, we're using it with the first derivative, and it's where the first derivative is equal to 0. So what we're going to do here is find the critical points. So C is just a critical point. So what we're going to actually do with the critical point is plug it into the second derivative. So this step is saying we're going to plug the CP into the second derivative. So what will that tell us? That'll tell us one of three things. So it's going to tell us first, if you plug the critical point into the second derivative and you get a negative value, think about what is the second derivative telling us? It's talking about concavity. So if you go ahead and plug the critical point in to the second derivative and you get that is negative, you are actually have a scenario where you're going to be concaving down, but you'll have a local max, because again, that's where a critical point is. So if you take the critical point, plug it into the second derivative, get a negative value, you have a local maximum. No need to check a bunch of points in between. It just immediately tells you, because it's a critical point, you have an extrema, but because it's the second derivative, it's concaving down because it's negative, which means it's a max. In the same way, if you were to take the critical point, plug it into the second derivative, and then you got a positive value, you have a local min. Be a little bit careful there, because if you think about negatives, negatives seem to be low, so min, but that's not the case. Negative value means that it's concaving down, meaning you have a max. Positive value means you're concaving up, which means you have a min. The downside to this test is that if you get 0, because 0 has no sign, it's positive and negative, or it's neither, it has no parity or no sign, it's really, we'll see what it says right here. It says that the function may have a max, min, or neither. In other words, the test is inconclusive. So it's one of those that if you have an easy enough function, it's easier just to plug it into the second derivative than go through the first derivative test. But sometimes plugging it into the second derivative may get you nothing. So in summary, plug the critical points into the second derivative, but just be aware that the test may be inconclusive. That is to say, you don't get an answer from it. You just may have to go back and use the first derivative test. So let's go ahead and let's actually not do the one at the bottom, because a quartic function is a little bit boring because it just is a parabola with a little bit flatter base. So it's again, it has the end behavior that's up, up. So let's go to the next one and actually look at how to use all of the derivative tests as a quick summary. So I have the graph over here. It's not in the notes, but again, I just added it so we have it for reference. But remember that whenever you have an odd function with a positive leading coefficient, its end behavior is going to be down to the left and up to the right. A little bit of pre-calc review, but that's what we're getting ahead, or we're kind of leading to in curve sketching. So let's go ahead and actually do the second derivative test to find local extrema. So again, there's 3 tests. Let's go ahead and first start by doing the second derivative test for local extrema. So this is the one I just talked about. The one at the beginning of this lesson, I'm going to go ahead and just kind of break this page up into 3 pieces. The middle piece will be the second derivative test for concavity. So this is what we did at the beginning of the lesson. And then lastly, we have what we did last class, which is to say we have the first derivative test for local extrema. And what we're going to see is that the first derivative test for local extrema and the second derivative test for local extrema give us the same extrema in this case. Of course, like I said, this test may be inconclusive. Let's go through it now. So the second derivative test for local extrema. Second derivative, I'm going to need to take two derivatives. So let's see, f prime is going to be equal to 3x squared minus 3. F double prime, oh, hold on, I'm going to actually pause right here. Remember, for the second derivative test for local extrema, you do need your critical points. So again, to get your critical points, you just set this equal to 0. You get 3x squared equal to 3, divide by 3, and then take the square root, you get x equals to plus or minus 1. All right, so those are my critical points. What I'm going to now do is take those two critical points and plug them into the second derivative. So let's take the second derivative now. F double prime of x is equal to 6x. Okay, so now let's go ahead and plug these in for, plug these critical points in. F double prime of my critical points is what I'm about to do. So f double prime of -1 is equal to 6 times -1, or -6. Oh, great, that's not 0. So what does this mean? This means, here, I'm gonna go put it down here. This means that we actually we're concaving down, so we have a local max at x equals to the critical point, -1. Again, if we want the actual value, we would have to plug it in, but you can see that over there. At x equals -1, we have a local max. In the same way, f double prime of 1 is equal to 6 times 1, which is 1. And again, that's positive. So what does this mean? It's concaving up, so there's a local min at x equal to 1. Little typo here, 6 times 1 is 6. Got a little quick there. But you can see we actually have a local min right there. So let's go a little bit out of order. Let's actually do the first derivative test again. Again, this was from section 4.3, but it should give us the same answers we got over here. And it will, but let's just go through it to make sure we see that's the case. So we actually already have our first derivative. F prime of x is equal to 3x squared minus 3. And we found our critical points, which are equal to x equal plus or minus 1. So for the first derivative test, we break the domain up into 3 pieces. So we broke it up from -infinity to -1, from -1 to 1, and then from 1 to infinity. Based off of the 2 critical points, we broke it up into 3 pieces. Let's now place a value into our derivative that's in this domain. So f of -2. So of course, if you look at this and just simplify this, plug -2 in here, you get 4. 4 times 3 is 12, and minus 3 is 9. So this is going to be equal to positive. So we're increasing. In the same way, if we were to plug, let's say, f prime of 0, or we were to plug 0 into the original derivative, not the original function, but the derivative right here, we would get a negative. We'd get minus 3. So again, I don't care if it's -3 or how negative it is, I just know that it's decreasing. And then let's go ahead and do f prime of, let's say, 2. This is also going to be increasing. So this, of course, is our first derivative test for local extrema. Because we switched from increasing to decreasing, we actually have a max right here. And we switched from decreasing to increasing, we have a local min right there. And of course, that is consistent with what we found, that -1 is a local max, and that +1 is a local min. And of course, to find the value, you would actually plug it back into the original. So then, of course, the last derivative test, the one that we introduced at the beginning of this lesson, was the second derivative test for concavity. So this is behaving very similar to the first derivative test. We just are going to use the second derivative instead of the first derivative in this step. So let's take one more derivative. F double prime of x is equal to 6x. Set 6x equal to 0. You get x is equal to 0. And this means that 0, f of 0 is a possible point of inflection. It's not an actual point of inflection until we guarantee that concavity changes. So to see the concavity that it changes, let's consider the domain up into two pieces based off of x equals 0. So negative infinity to 0 and 0 to infinity. Plugging in the value in here, let's just say negative 1. Again, we actually already did this computation on the left. We see that it's going to be equal to negative 6. So we are concaving down. It's concave down here, or just concave down. And f double prime of 1 is equal to 6. So this concaves up. So you can see right here, what is happening is that we have a switch in concavity. So that means that we actually have a point of inflection, which in this case would be 0, comma f of 0, which in this case we simplify plugging 0 into the original is just going to be 5 because we have the original. This is going to be 0, 0, 5, and you can even verify that graphically right here. So those are the 3 derivative tests. And if we combine these derivative tests with what we learned in pre-calculus, we essentially have a way to make perfect graphs. We're not going to go too much into detail with this, but it's one of those things like it allows us to go ahead and kind of figure out all the local extrema along with the ideas from the first that we learned first in pre-calculus. So we'll highlight a few of these ideas, look at an example or two, and then that really completes the conversations about the derivative tests. We will use these again in 4.6 for optimization, but let me just pause briefly to see if there's any questions. And again, if you're watching this, pause just to kind of take a mental break and just to see if you understand everything that's happened so far. So again, a quick little review of things we've learned already. Like at the even at the beginning of the semester, we talked about identifying the domain and looking at symmetries, like if functions even or odd. So this right here, good to have in mind, but honestly, if I remember the homework correctly, you really mostly focus on the derivative tests. So that is to say, part 2, you would find the derivatives. Part 3, you would go ahead and find the critical points. And apply the first derivative test. Part 4, you would again just be working with the first derivative test. Part 5, you would be doing the second derivative test for concavity. This goes back to what we learned in 2.6 using asymptotes, so in phrasing them in terms of limits. So we could really go into detail. And then of course we could plot some key points such as like the x and y intercepts, the possible points of inflections and things we found in the derivative test here. But again, we've done a lot of work if you gotta think about the big picture between calculus and pre-calculus. But if I were teaching this lesson in class, this is typically where I just pause and give you some time to go ahead and try number 7. Example number 7, and the main thing I would focus on or ask you to focus on is just those 3 derivative tests. So again, if you're watching this and really just kind of engaging with the content as you go through it, I would say go ahead and pause the video and just see if you're able to do those same 3 derivative tests on this one. All right, so let me put up the solution. The solution would be right here. So again, you can see the first derivative test for local extrema. I'm just using the first derivative. The second derivative test for concavity, similar in nature. I'm just using the second derivative with the possible points of inflection. And they do come out to be points of inflection. And the second derivative test for local extrema, notice here that is inconclusive one of those cases. So you still actually need to verify that 0 is not an extrema. The second derivative test being inconclusive is not enough to say that there's no extrema. You still need to use this one. So again, this, of course, you could also use some sort of graphing utility to verify your answers, and the answers are, you can verify down here below. I would encourage you to pause just to verify that. But let's go ahead and consider a scenario like in number, let's see, let's go back to the one that's not filled out. Let's go ahead and consider a scenario like this one right here. So in this one, we would not be able to use a graphing utility to its fullest, because notice that what we're given is the first derivative. So let's read through this and just talk how the general curve sketching method will allow us to go ahead and understand the shape of this graph just purely by using the derivative tests. And I'm not even going to do the derivatives test in its entirety, but just to kind of highlight certain important things. And of course, I encourage you to kind of work through the details yourself. But the first derivative of the continuous function is given to us right here. I'm going to go ahead and rewrite this as x cubed minus 3x, just distributing the x, just to make it a little bit easier to work with in terms of finding the critical points, finding the second derivative and the like. So we're asked two things. We're asked to go ahead and find y double prime and then sketch the general shape of the graph. I'm going to even add a few more thoughts. So one thing that we could remember if we looked at 4.2 and bring those ideas back into play, we actually could get one of the possible functions with this derivative. It is possible that well, let's just maybe notice this first. If we were to think backwards, realize that the antiderivative, as we'll define formally in 4.7, but thinking backwards, y is going to be x to the fourth minus 3x squared over 2 plus some constant c. So if you, again, think backwards, take the derivative of this, you would get the x cubed. Take the derivative of this, the 2's would cancel, it gives you the minus 3x. And we don't know what constant c there is because, well, of course, any constant when you take the derivative goes to 0. But we do know, and this goes back to some ideas from pre-calculus, that because this is quartic, that is to say it is x to the fourth, it's an even-powered function with a positive leading coefficient, we do recall that the end behavior is going to be increasing both on the left and the right. So what I'm going to go ahead and do is just take some of these things that we talked about and maybe just sketch a graph as we go. So let me go ahead and just put a blank x and y axis up here. And I know from what I just did, thinking about backwards, my original function will have end behavior that looks like this. So I'm just trying to sketch the general shape. Maybe I just wanted to identify it using information from the first and second derivative. So let's go ahead and actually find our critical points. So what we can go ahead and do is take our y prime and set it equal to 0 to find our critical points. So x times x squared minus 3, set this equal to 0. X is equal to 3, x squared, x is equal to 0, and x squared minus 3 is equal to 0. We find our critical points are x equals 0 and x equal to plus or minus the square root of 3. So again, plus the square root of 3, I think is approximately like 1.5, maybe 1.6, somewhere there. It's somewhere between 1 and 2. Just thinking my square root of 1 is 1 and square root of 4 is 2. So this is, I don't know, let's just say it's 1.5. So let me add some scale to this. So just kind of adding some information. Let's scale this graph. Let's say this is 1, and let's say this is -1, and this is -2. And this is 1, and this is +2. So what we do know is that, let's see, 0, so at 0, at maybe approximately 1.5 and -1.5 are going to be local extrema. So there's going to be some local extrema. And again, I just want to get maybe a general idea, but of course we haven't done the test in its entirety. But so I'm just going to kind of say, okay, maybe if I'm looking at a graph in a lineup, can I identify which one is my correct original? The other thing I'm going to look at is possible points of inflection. So I'm going to do y double prime, set that equal to 0. So let's see, what is y double prime? I'm going to take the derivative of my original, not my original, the derivative of what I was given. I was given the first derivative. So y double prime is 3x squared minus, nope, let's try that again because of multiplication. No, yeah, that was good, 3x squared minus 3. I don't know where I was thinking there was a 2 there. Anyway. So let's now set 3x squared minus 3 equal to 0. Add 3, divide by 3, take the square root. Again, some fairly straightforward algebra. You get x equals to plus or minus 1. So what I now know is at plus or minus 1, these are possible points of inflection. So again, I could continue and maybe go a little bit more deeply into the actual test, but I'm just trying to sketch it. A possible point of inflection, so right here. So if I'm kind of just thinking about the behavior that I know from pre-calculus, what I think would be a good option would be, let's see, I need some sort of minimum. I'm going to go ahead and say maybe there's a minimum right here. Then I'm going to be increasing, and notice I'm concaving up at this point. But at 1, I want to start concaving down. So I'm concaving up here, concaving down here. And again, let's just say that this is a critical point here at 1. So again, that's maybe an extrema. So let's go ahead and just kind of have the graph look like that. Again, at 1, I'm going to change my concavity. So this part right here, I'm concaving down. But at 1, I'm going to go ahead and start concaving up. So it starts kind of scooping up. Let's have another extrema right here. And then we'll go ahead and have something like this. A few other things you may have noticed is the fact that our original function is, could have pointed out earlier, this is actually even. Because if you plug in -1, notice again, you get back the same function. So we have this idea of symmetry in place. There's the reflection over the y-axis. So you have the idea of symmetry. So again, a lot of the ideas come together to go ahead and give us some general techniques to understand a graph and even get perfect sketches. But this again just ties together some of the ideas. The one down here below is very similar to the one that we did at the end of the last lesson, but it's in your homework, so I encourage you to take your time. It really is a good exercise to make sure you understand all of the concepts from the derivative tests, and it allows you to find the constants in front of the different terms. But that right there are the 3 derivative tests, the second derivative test for concavity, the second derivative test for local extrema, and the first derivative test for local extrema. We will use these again in 4.6 in applications such as optimization. But in section 4.5, we will use the derivative to understand how to find limits. So again, if you're a little rusty on limits, it may be worth just looking back through those before you go ahead and do 4.5. But good luck with everything. If you have any questions, let me know.